Hello everyone, welcome to our new session, that is Geometrical Isomerism. Today we are going to learn some other topics in Geometrical Isomerism, that is Stereoselective and Stereospecific reactions, also the Stereochemistry of biphenyls. First one, Stereoselective and Stereospecific reaction. See, this is an example. We can start with an example. There is reaction of alkene with bromine. So this is 2-butane. So it will react with bromine and we'll get 2,3-dibromobutane. Here you can see there are 2 chiral centers. So they can exist in 4 isomers. That is, one pair of enantiomers and others are mesomers. And they can also exist as diastereomers. They may be cis or trans. See, this is cis-butane. When they undergo reaction with bromine, we can get 2 enantiomers. This is not mesomers, this is enantiomers. So, these type set of stereoisomers formed exclusively, that is called stereoselective reaction. Then in the case of trans-butane, when reacting with bromine, we'll get pair of mesomers. So this is also stereoselective reactions. So here the pair of mesomers are only formed. Next, in the reaction of this alkene with bromine, that is, the stereochemistry of the product depends upon the stereochemistry of the substrate. And the reactions, that is the stereochemistry of the product, that is determined by the stereochemistry of the starting material. This is called a stereospecific. So that is this is the starting material. Actually these products depends upon the stereochemistry of the starting material. So these type we can call it as stereospecific reactions, and these are always dependent both, as we seen in the previous example. So the reaction of the alkene with bromine is also stereospecific. They are stereoselective and stereospecific in nature. We can see the example, that is in cis-2-butane substrate. When the reaction with this bromine, here we are getting cis-bromonium ion, and they are dividing into 2 parts. This is B and this is A. So that is, we will get 2 enantiomers. It is racemic 2,3-dibromobutane. Likewise, this is the explanation. First one is the formation of the cis-bromonium ion. This is cis-bromonium ion formation. And next step, that is attack of bromine to this bromonium intermediate. And they have 2 possible pathways which have equal probability. So if attack follows the pathway, the structure A is formed. If it is in pathway B, the structure B is formed. So these both pathway, they having same level of the probability. So A and B, there is a pair of enantiomers, they are formed in equal amount. That is the racemic mixer. See, this is the explanation of this. So these are equal probability. So they are racemic mixer. Next is in the case of trans-2-butane. See, when they undergo reaction with this bromine, we will get trans-bromonium ion. And as we discussed earlier, there are 2 pathways, that is C and D. When reaction occurs here, they will form product. And when D, they results in another product. But these are meso 2,3-dibromobutane. So all stereospecific reaction, they are stereoselective, but all stereoselective reactions are not stereospecific. So that means we can say that the stereochemistry of the product, it depends upon the stereochemistry of the substrate. So here only one type of isomer is produced. Sometimes if any type of isomer is produced, then its stereochemistry may depend upon the stereochemistry of the substrate. Example, this one, synthesis of 2,3-dibromobutene from 2-butene. It is a stereospecific reaction. Hence, it is also a stereoselective. So again, I am repeating the same thing, that is all stereospecific reactions are stereoselective, but all stereoselective reactions are not stereospecific. Next one, that is the stereochemistry of biphenyls. See, biphenyls are the compounds where the phenyl ring, that is the phenyl ring is connected to another through a sigma bond. So you can see it from figure. This is the biphenyl structures. That is, in biphenyls, the substituted biphenyl, there will be freedom of rotation through a single bond to allow the interconversion of the various conformers and rotomers, so that the various rotomers cannot exit independently. See, this is single bond, so there will be a rotation between the single bond, so they results in various conformers and various rotomers. See, usually the biphenyls means these are the large substances, and they usually will be at ortho position, that is on the either central sigma bond. So there will be, because of this, there will be a restricted rotation along with this due to steric hindrance. So there will be always, most probably there will be in the ortho position. So near to that sigma bond. So rotation will be restricted. So this is mainly due to the steric hindrance. So if substituents are different, the chiral molecule can exist as the pair of the enantiomers. So that is, if the substituents are different means they can exist as a pair of enantiomers. We can call it as atrophy isomers. So same thing here explaining, that is the freedom of rotation through the central single bond. So there will be various conformers and rotomers that cannot exist independently. And when the large substituents at the ortho position, that is at the central sigma bond, experience restricted rotation along with this bond due to steric hindrance. Also, if the substituents are different, they can exist as the pair of enantiomers. We can call it as atrophy isomers. See, polynuclear aromatic systems, just binol, they can exist as enantiomers. See, this is the example of the enantiomers. And this is the specific rotation of this two. Then atropism, these are the stereoisomers due to restricted rotation about in a single bond. Then these stereoisomers, that is due to this restricted rotation or hindered rotation about the single bonds, there will be some steric strain due to the high enough to allow for the isolation of the conformers. So because of the steric strain, that is why they results in the hindered rotation. Then if bulky group, that means large groups around the ortho position of biphenyl or strained ring structural features, so they may increases the barrier. There is a rotation between these two distant conformations. So This is the criteria of observation of the entropy isomers. So we can call it as also axial chirality. So chirality means it is not simply a center or a plane, but it is an axis. So you can see sigma sigma bond. It is also known as pivotal bond. That is a chiral structure of a biphenyl. Then that is when biphenyl substituted on the ortho position, which contains chiral axis along with this biphenyl linkage. So they are perpendicular to each other in order to minimize the steric strain between the substituents. So rotation about this biphenyl derivatives along with this pivotal bond is restricted. So you can see that this is a biphenyl substituted derivatives. They are on ortho position along with the chiral axis. So they are perpendicular to each other because in order to reduce the steric strain between these four substituents. So their rotation will be restricted. So these are the examples of this. Next one, conditions of the tropism. So this should be stable axis. Then there should be a presence of different substituents on the both sides. Then configurational stability is mainly determined by some factors. We can see that factors. First one, that is steric demand. Next is length and rigidity of the bridges. Next one, of course, is rotation, restricted rotation. It is, for example, photochemically or chemically induced process. Then stereochemical assignment of the biphenyls. See, this is the figure. So determining the stereochemistry of biaryl atropamers by the use of Newman projection. That is, using this Newman projection, we can explain the stereochemistry of this atropamers. That is the ortho. In some cases, meta substituents are first assigned. In some cases, meta substituents are first assigned. This is due to one rule, that is can in gold pre-gold priority rules. We have already discussed in our first chapter. That is because of according to that rule, that is we usually start with the substituents with high priority. Out of these four substituents, who having high priority, we'll give more importance to them. So the high priority will be in the closest ring. Then moving along with the shortest path to the substituents of highest priority to the another ring. So the absolute configuration is assigned, that is P or delta 4 clockwise and M or delta 4 counterclockwise. See, this is the Newman projection examples. See, this is counterclockwise, that is M. This is the biphenyl derivative and there are four different substituents in it. Likewise, this is clockwise. So this is counterclockwise and this is clockwise. So the biphenyl will be like this. This is counterclockwise, you can see. Then chirality in biaryl components. So this is Newman projection and they are going counterclockwise. So it will be like this. Then another example, they are going in another way. So it will be like this. It is clockwise. It will be like this. That is P means clockwise, M means counterclockwise. So the Newman projection will be like this. Is after clockwise rotation, it will be like this. After counterclockwise rotation, the Newman projection will like this. Based on the rotation, we will decide the substituents, that is where it should be in the compound. So this is explaining here. We have already explained it, that is the biaryl entropias that can be explained by using this Newman projection. So we always consider ortho position only. Sometimes we used to consider meta substituents due to this rule, that is can ingold prelock priority rules. So according to that rule, that is the high priority substituents, they will move along with the shortest path, that is in the another ring. So the absolute, based on that, they will decide the configuration, whether it is clockwise or counterclockwise. And that's for today. Thank you.